All right, welcome back to our third installment of Astronomy 1299. Today I want to take a look at Kepler's laws and the relationship between Kepler's laws and the kind of research that we're going to be doing in terms of plotting elliptical orbits of binary stars. I also want to look today a little more at the motions of stars in the sky and how those motions work so that we have a better understanding of where our research is taking us and how our data is being gathered and what the usefulness of the data is, and just in general the significance of the research that we're about to do. And so this introductory material is designed to give you a better intuitive and um, quantitative feeling for the um, information that we're going to be gathering, and just to give you a research quality background so that you know the significance of the data and um, how it relates to things that are important in science. And so I sent out a message. I don't know if everyone received it or not. I think I sent it a couple hours ago, but we had a couple of people who have had a hard time adding the course, and I'm not sure why that has happened, but been able to connect three of you to the Canvas website, and so that you can work on the subjects, and then we're expecting that the late ad forms will be sent to me very soon, within a few days. And as soon as I get them, I'll sign them, and then you'll be officially in the class. Since last week, I've added a couple more quizzes to our Unit 1 material, and I'm expecting that we'll continue with Unit 1 this week and possibly through next week, although I would like to get started with Unit 2. So possibly toward the end of um, the discussion next week, we'll get going with Unit 2. But there's a fair amount to cover just to give you a good background. And so that's my goal for today and for part of next week. Are there any questions on anything that you've encountered so far that you want to talk about? If you have questions and you want to talk to me personally, remember that I do have my Zoom office hour 5 to 6 on Monday, and I'm available after the class is over to talk with any of you. Um, and I also have 4 other contact hours in person at Cuesta College during the week. Okay, so let's go ahead then. If you recall last time, I went through the history of astronomy, very brief history of astronomy, up to Kepler's laws of planetary motion. And so those laws of planetary motion involve the actual motion of uh, objects around each other. And so this is critical to the kind of data that we're going to be gathering, since we're going to be looking at the elliptical orbital patterns of binary stars. And so let me share the screen and do that. Let me just see if I can pull this up on the screen. Okay. So what we established last time was that Kepler basically made an important paradigm shift in which he went from the belief that objects had to be in orbits that involved perfect circles to the idea that an ellipse could be a perfectly viable way of expressing a real life situation. And so he analyzed the motion of the planet Mars, and he didn't have any idea why the orbit would be elliptical, but he was a good uh, mathematician. And so he was able to take the information uh, that Brahe had collected on the planet Mars, and he was able to demonstrate that the orbit was elliptical. So the basic idea with an ellipse is you take two fixed points, and the distance between those two fixed points has to be a constant for you to draw an ellipse. So a simple way of explaining that is to just take a closed loop of string and have it be bigger around than two nails that you pound into a board. And then you can stretch the string out, and by keeping the string taut, the sum of the distances between those two fixed points will always be the same. And the curve that you'll draw will be an elliptical orbit. Now, there are also some mathematical equations associated with this, but the important thing for us here is to realize that the farther apart these 2 points are, the more elongated the elliptical orbit will be. And so as we analyze the orbits of stars, we will be looking at what kind of an elliptical path the um, the stars are moving in. And this will give us important information about the mass of each star, the lifetimes of the stars, and um, other important aspects of whether or not they might have planetary systems and uh, many other applications as well. And so if we look at different kinds of ellipses here, we see that if both points are at the same location, we have what's called a degenerate form of an ellipse, which is a circle. So a circle is actually an ellipse where both focal points are, or both fixed points are at the same location. So the Earth's orbit is similar to that around the sun, because the two fixed points are not that far apart from each other. So that the Earth in its orbit um, comes within 91 million miles away on January 5th and 95 million miles away on July 4th. And so that averages out to 93 million miles, but it's a fairly circular orbit. As the two fixed points become farther apart, then the orbit becomes more and more elongated until you can have an extremely elongated orbit. And this would probably correspond more to the kind of orbit that you'd see from a comet going around the sun. So the kinds of orbits we'll be looking at will be fairly elliptical. Because um, the central object in Kepler's formulation, the central object was the sun, and the sun was located at one of the focal points. And the other focal point is just a mathematical construct. In our situation, what we're going to have is the major, more massive star will be at one focal point, and then we'll be plotting the orbit relative to that more massive star of the less massive star as it goes around. And so there's a quantity called the eccentricity, which gets larger and larger as the two focal points become farther and farther apart. And so this aspect of the orbit can also be determined by plotting enough points on the orbit. And so there are different kinds of what are called conic sections that can describe different sorts of planetary orbits. We've got the circle, which is a conic section in which you basically take a cross-section of the cone that's parallel to its base. An ellipse, if you take a cross-section of the cone that's at a little bit of an angle, this is the kind of orbit that we'll be looking at the most in this class. Hyperbola and parabola are not closed orbits, but are open orbits in which the central object remains somewhat fixed, and the object that's coming in makes only one approach and never comes back again. Okay, and so let me just, if I can, in the shared screen mode, let me go to some of the animations that are available to you, and these are right down there in the Kepler Law section. The first one that I wanted to show here, we've got a in this case it's a star, and then here this could be either a planet or a second star that's going around. But notice that the star is at one of the focal points. The other focal point is not shown. And so I'll go ahead and start this. Now, the length of this arrow, let me just stop here for a second. The length of this arrow represents the speed of the orbiting star. And so we'll notice that as it gets farther away from the focal point, the speed slows down. And then as it comes in closer, the speed increases. And so you'll be able to note that by the length of this arrow, the length of that arrow should get shorter as this gets farther away and gets longer as it gets closer. So there it is slowing down. Now, the reason it's slowing down here is that it's farther away from the sun. And we'll see later that this is partly due to the fact that the gravity force is weaker at this distance away. That this object will turn around and then it will essentially fall toward the central object and pick up speed until it gets to its point of minimum approach. Then it'll slow back down again. The difference in the speed has to do with the ellipticity of the orbit. The difference in the speed is zero if it's a circular orbit, but if it's a very extremely elliptical orbit, like a comet, it might be going so slowly at its more distant point that you could walk alongside of it. But when it's at its closest point, near the sun, a comet could be going hundreds of thousands of miles an hour. And in the cases we're looking at, the two masses are more comparable to each other. So this is going to give rise to a difference in speed, but it won't be as elongated an ellipse as we looked at in one of those previous slides. Let's see, where was that? Oh, there it is. I think we had it over here. There it is. Are there any questions about that so far? That's just the basic idea of an ellipse, without getting too heavily into the mathematics. Okay, well, let's move on to the second law, Kepler's second law. And again, he had no idea why these laws worked. It was up to Isaac Newton about 75 years later to basically invent the laws of physics. Newton had some problems that he couldn't solve, and so then he invented calculus so that he could solve those physics problems. That's why he invented calculus, was to solve physics problems, and he had essentially invented, or I guess we could say discovered, physics. So a little later on, we'll talk about Newton, and Newton made sense out of Kepler's laws in terms of mathematical and physical principles. But Kepler came up with the correct laws just from observing the motions of the planet Mars. And so his second law is that planets sweep out equal areas of the ellipse in equal times. And this means that essentially the and this will also work for stars, of course, because when stars are orbiting around each other, they follow the same kind of elliptical orbits. When a star gets closer to the larger star, it's going to be moving faster. We saw that before. And so the fact that it moves faster means that it travels through more of this arc distance. But if we think of it in terms of an area of the ellipse, the base sides of the ellipse are smaller, but it makes up for it by this faster distance that it travels so that this area equals that area. So let's say that this distance from A to B happened over 1 month, and this distance from C to D also happened over 1 month. Then we can say the area of this part of the ellipse here, swept out from A to B, equals the area swept out here from C to D. Another way of saying this is that the planet moves faster when closer to the central object and slower when farther away. So we can see that with this next simulation here, and you have these all available to you in Unit 1, so you can check these out as well. We'll notice here that in equal times, these are measured out as equal times. We're sweeping out equal areas. And so that's Kepler's law. And so by getting a sense for the ellipse, by plotting out enough points on our elliptical path, it'll be possible to extrapolate and determine the shape of the ellipse, how fast each star is going at each point, what the mass of each star is. And so it's really a fairly significant discovery to be able to do this for a star system. And so there will be a few points that will already have been plotted, and then we'll plot another point because we'll have waited enough time so that there's a reasonable gap in observations, and then we'll plot another point. And so maybe it's our data that will show this is an ellipse. Another possibility, though, is that we might be looking at a visual binary, one that isn't actually gravitationally bound. We can't be sure whether our data is going to be corresponding to an actually gravitationally bound system, or one in which they're actually look like they're close together, but one is really a lot farther away than the other, and we just can't tell. But the way that we would know is if we follow along some of the plotted points, and the plotted points don't curve very much. If they just start to stray off like this in a straight line, then it looks like they're never going to come back again. And that means that it's probably just a coincidental alignment of two stars and not a gravitationally bound system. But again, if you do select one like that, and you're able to demonstrate that it's a visual binary rather than a physical binary in which they're gravitationally bound, that still is important to know. It's important to know whether they are real binaries or whether they're just optical binaries. And so that's still publishable data. Okay, so that's the second law. Any questions about that? So everything that we've talked about here with planets going around the sun is equally valid for stars orbiting around each other, except that you're just taking one of the stars, making that the bigger one, making that the central object, and then the other one is the one that you plot going around it. The sun in this picture is actually also moving a little bit back and forth. But that back and forth motion is not shown. And that'll be also the case for us. The central object will be moving as the other one goes around it, but we'll be plotting it in such a way that we'll just be looking at the motion of the smaller star around the larger one. And then Kepler's third law is written in terms of an equation, t squared equals ka cubed, where t, and we mentioned this last time, this is the period of the orbit. So that's how much time it takes for, in this case, that we're looking at, for this one star to go around the other. The A is the average distance of that star from the central star, and K is a constant. That's the same for any object that's orbiting around that central object. And the important thing here for us is that by getting the shape of the orbit, we can get A, And by measuring the amount of time between data points, we can get the period. And so that means that we can get K. And so, big deal. Well, why do we want K? Well, K relates to the mass of the stars. And so if we know K, then we can also determine the mass. Once we have the mass, that's really the only way that we know of that you can get the mass of a star is by studying its relationship to another star in orbital motion in a binary star system. And so this is critical information that we need to understand what's going on with stars. And so I've got a simulation here for let's see here. For the third law, this is another one that you um, that you have a simulation for. And so let me just go ahead and play this one. In this one, we have one star going around another. But notice off here on the edge, we've got the period squared plotted versus the distance cubed. Okay. And so if I were to change the mass, watch what happens when I change the mass. It moves along this straight line. And so if I move it in like that, then I've changed the mass and the period squared versus a cubed relationship changes again. And so by knowing, what I'm trying to demonstrate here is that changing the mass changes the period squared versus the AQ relationship. And so that's where the K comes in. By being able to figure out that K, that's how we can get the mass. And this is not something that is a mathematical operation that you need to do in this class. But by gathering the information, you can then give other scientists, or this might be something you would want to do yourself, say as a project for a master's degree, perhaps, or something, to determine the mass from orbital data that would be available from the kind of data that we're gathering. Okay, so are there any questions then about any of Kepler's laws or how that relates to what we're going to be doing? Okay, for our solar system, we have let me see here. This would be one that we could look at. For Mercury, we've got a period of 0.24 years and a distance of about 40% the distance from the Earth to the Sun. And so as we go to each successive planet, what we see here is that a bigger period means a bigger distance away from the Sun. And it's in an exact correspondence to the period squared equals some constant times the distance cubed. And so as we get to bigger distances away, Saturn is 20 times the distance from the Earth to the Sun. I'm sorry, 10 times the distance from the Earth to the Sun, and has a period of 29 years. Jupiter is 5 times farther away from the Sun than the Earth is, has a period of about 12 years. Neptune, 30 times farther away, 164 years. So we see this general trend for the planets. The farther away they are from the Sun, the longer they take to go around the Sun. And the same thing it holds true for one star going around another. They're following the same laws of gravitation. But the reason that all this works is because of gravity. And so let's just go to Newton's laws of gravitation. And this is all in Unit 1, all of these slides, if you want to review them on your own, under the caption, How the Sky Works. And so you can pull up all of these if you think any of them are useful and you want to look at them more. And so what Isaac Newton was able to show, this is after Kepler, when he was trying to demonstrate that Kepler's laws of motion are valid, is that the force of attraction between two objects is a strong function of the distance. And it goes like 1 over the distance squared. And so what that means is that if you're 1 unit away from another object, and then you double that distance, the force goes down by a factor of 1/2 or 2 squared. It goes down by a factor of 2 squared or 4. So doubling the distance away decreases the force by a factor of 2 squared or 4. Tripling the distance decreases the force by 3 squared or 9. Quadrupling the distance decreases the distance by 4 squared or 16, and 5 times farther away than your original distance would decrease the force by 1/25. So if you were to, let's say, climb a ladder that was the radius of the Earth away from the Earth, so that you could get twice as far away from the center of the Earth, your weight would only be 1/4 as much. So let's say you weighed 160 pounds on the Earth, and then you climbed up a ladder that was the radius of the Earth, 4,000 miles high. That would double your distance away from the center of the Earth. And that's what we mean here, the distance between the centers of the objects. And that would decrease your force from 160 pounds to 40 pounds. And so you'd be only 1/4 the weight at double the distance. And so we see then that this is a very strong dependence on distance with gravity. And so this is why in the elliptical motions, when one star gets closer to another, it starts moving a lot faster because there's a lot more gravity, and the gravity is pulling on that object much harder, and that speeds it up, and then it kind of whips around, and then it slows back down again as it gets to distances that are farther and farther away. So you have a simulation that will allow you to play around with that as well. That's in here's actually the different selections that you have. And so what I've been looking at here is right in these PHET simulations for Kepler's laws. And then I'm also going to look at one now that's on gravity in orbits. Coming up. This is it right here. Okay, so let me just play this. We can see what's happening. Okay, let me just move it a little farther away. Oh, stop this. I think you can, these are adaptable. Yeah, you can pull them a little farther away if you want to, so that these arrows don't overlap. So these arrows then represent the force of gravity between these two objects. And you notice at this distance away, the arrows have a certain length. But now look what happens if I move them in closer. Those arrows get much longer, 4 times longer if I move it in twice as close. Whereas if I move it away twice as far, the force gets 4 times less. And so just doubling or halving the distance changes the force by factor of that squared. And so it's a very, very strong dependence on distance with gravity. And so it's gravity that makes these elliptical orbits work. When Newton was able to solve his equations, he actually showed that the equations gave rise to elliptical orbits, but that required what we call an inverse square law for gravity. And so as we look at these orbits, and here we're showing, oh, that actually made that go a little too far away. Is it gone? Let me try to speed this up a little bit. Pulled it too far away, and I think I may have thrown it into an open orbit. So I'm not going to mess around with this too much right now, but this is these kind of simulations are things you can play with. You can make the mass bigger, smaller. You can show what the force of gravity looks like. But probably what I want to do here is just reset this thing. Okay, so that was the reset button. That's an important one. And so as this thing goes around, you can look at the velocity, you can look at the gravity force, and you can look at the path. And so that gives you maybe a little better feeling. And then as it comes in a little closer, notice this is an elliptical orbit. And so this is how fast it's going. This is the force of gravity. And so as it gets in closer, that force gets bigger. And as it goes a little farther away, that force gets smaller. And so again, that's another thing that you can play with just to get more of an intuitive feeling for how all of these relationships work. And so the weight of an object then can take on any value. The weight of an object on the moon is only 1/6 of its weight on the Earth. It depends not only on the mass of the moon, which is less, but also on the radius. If you got near close to Jupiter, you'd be 2.5 times your weight on the Earth. And if you were near a neutron star, your weight would be 100 billion times your weight on the Earth. And so these relationships then hold throughout the universe. And so the idea with orbital motion is that you have a balance between the gravity force, which is pulling in, and the natural tendency of an object to want to travel in a straight line. And so those two effects tend to compensate for each other when one object is in orbit around another. So you have the gravity force here, you've got the planet's velocity in a sideways direction. And so what causes the orbital motion essentially is a balance between what we call inertia and gravity. So here, what we can see is that once we understand what gravity is, we can say, well, if I just drop an object, it's going to fall toward the Earth. But if I throw an object straight away and there's no gravity, then it's going to get farther away from the Earth. And so there's a balance then between the object wanting to get farther away from the Earth by moving sideways and falling toward the Earth because of gravity. And so if you can balance that out just right, then an object that is falling toward the central object will keep missing that object because of its sideways motion. And so when you see people up in outer space, like in the International Space Station, um, floating around and waving to their family, and they look like they're completely weightless, you go, oh, well, that must be the inverse square law, that they're just far enough away from the Earth so that the gravity force is essentially zero. But no, that's not the case at all. At that height away, they are um, maybe 99% of their weight still, because they're not that far away from the surface of the Earth. In relationship to the radius of the Earth, they're like maybe 200 miles up. And the radius of the Earth is 4,000 miles, and they're only 200 up. So when you do the inverse square law, their weight is still about 98%. The reason that they seem weightless is that they're in free fall. They're falling toward the Earth, but they keep missing the Earth because of their sideways motion. And so that's the critical thing with orbital motion. This is why two stars orbit around each other. It's a balance between the falling motion and the sideways motion. The sideways motion tends to move you farther away without gravity, but with only gravity and no sideways motion, you tend to move toward. And so the net effect of both of those together is a combination of the two. And so let's say here we have a central object, and then here's our orbiting object. So that object moves a certain distance this way. Let's say that you're near the surface of the Earth and you fire an object at 5 miles per second. That's about 17,500 miles an hour. Well, if you fire it away from the Earth at 5 miles per second, and we're doing this above the Earth's atmosphere, so we don't have atmospheric drag, in 1 second, it'll be 16 feet farther away from the Earth. But that 16 feet is exactly how much the object will fall in free fall because of gravity. And so it gets 16 feet farther away at 5 miles per second, moving away from the Earth, but it falls that exact same amount in the same amount of time. So that the inertial motion and the falling motion just balance out. In the next second, 5 miles, 16 feet, 5 miles, 16 feet, 5 miles, 16 feet, 5 miles, 16 feet, all the way around until about 90 minutes later. That's how long it takes for an object to orbit the Earth. You'd have to duck because the thing would hit you in the back of the head. And but it doesn't do the sideways motion and then the falling motion. It does both of them at the same time. So that smooths out the jaggles in this curve and gives rise to a smooth orbit. If it's perfect, so that your sideways motion and your falling motion exactly compensate for each other, then you have a circular orbit. But if it's not quite perfect, then you still get a elliptical orbit. And so elliptical orbits are much more general because they don't require that perfect balance between the falling motion and the sideways motion. And so that, of course, is the kind of thing that we normally expect to see, is that one object is in an elliptical orbit around the other, rather than it being in a perfectly circular orbit. Perfectly circular orbit is going to be more common if one of the stars were way, way, way more massive than the other. But if that were the case, we wouldn't select that binary star system, because one of the stars would show up on our picture and the other one wouldn't show up on our picture. We wouldn't be able to get a good picture of it. So we'll always be looking at stars in our data in which the masses of the stars are fairly close to each other in magnitude. Are there any questions about that? I hope that that's clear. I'm not going too fast. Okay, what I'd like to do next is to look at motions in the sky. And so let me just go back to the beginning of these PowerPoint slides that I have here. And there are a few things that we talked about briefly. I'd like to look in a little more detail at them today. We talked a little bit about constellation patterns as being fixed patterns of stars that can be used as a coordinate system. And you can choose to describe a certain star pattern by any kind of shape, but we tend to go with what was thought of as being representative of that shape eons ago. And so this is Orion the Hunter. And so we might not think of that shape today, but these are important that the same grouping of stars, we are calling the same thing, so that we're speaking the same language. When we talk about constellations, we try to find things that everybody needs to agree on what we're calling the constellations. And so here we see that in Orion, even though the stars look like they could be at comparable distances, they're actually, most of them are quite a distance away from each other. And so this is, in a physical binary system, this is the kind of thing that can happen. You see one star, looks like it's really close to the other, but in reality, they're just coincidentally aligned and they have a small angle from our point of view between them. But one of them could be much brighter and be farther away. This one could be dimmer and be closer, and they could both look like they're the same brightness, and they could look like they're very close to each other. And so that would be a case where we'd be looking at a optical binary, uh, kind of a trick of the eye, rather than a true physical binary. And in our coordinate system for the sky, the North Star is the central point that doesn't change. And so everything else in the sky tends to describe motion about the North Star, but the North Star is the one point in the sky that remains fixed. And the reason for this is if you were to look at the North Star, you would need to, there's a couple of ways of doing it. You can find the Big Dipper and extend the pointer stars to the North Star. Or the easy way is to just go to the North Pole and look straight up. Then it's just right there. Now, of course, it's not easy to get to the North Pole, so maybe this actually is better to find the Big Dipper and extend those lines to the North Star. And so let's just go to, we have a simulation here that helps us see what's going on with the sky. This is our interactive star chart. So you're welcome to pull this up anytime you want. And so what this
I
does
don't think you
basically,
could see it. Are you sharing
you're not seeing it?
the interactive star chart
Yeah.
on the screen? I don't think you're sharing it. I still see the drawing from,
Oh, sorry.
yeah.
I need to, thank you.
Yeah.
Thank you. I need to go back here and get into, okay. How's that? Is that
It's
good?
good now. Yeah,
Okay.
looks
Thank you. Yeah, I forgot to switch a while back. I hope that I didn't go through too much of this without the visual that you needed. So here we have um, this is basically all of the sky that you can see. Here's the Big Dipper there, which we saw in the last picture. And then we have the pointer stars pointing to Polaris there. Okay, now the way that we would find Polaris here in our location in San Luis Obispo is we would need to look toward the north and look up at an angle that's equal to our north latitude. So our north latitude here is about 35 degrees. And so if you look to the north, I know the north is that way for me here. I look along the horizon and then I look up at an angle of about 35 degrees. I see Polaris and I should be able to find the Big Dipper. And so what I'm going to do here is advance this star chart, and this will represent the kind of motions that the sky seems to represent about the North Star. So I'll do this in hour increments. So we'll notice if you look here at Polaris, all the other stars seem to be moving, but Polaris is staying in the same spot. Can you see that? And then it gets to be daytime, so you can't see it anymore. So I'll go back here in 1 hour increments. But notice what's happening with the Big Dipper and all the other stars that are going around the North Star. They seem to be describing counterclockwise. Here I'm going backward in time, but if I then move again forward in time, notice that the Big Dipper is rotating around Polaris. So this is the kind of motion that the stars do. And all of these other stars also exhibit this kind of rotational motion. And they're not really moving. This is all due to the Earth's motion around the sun. And so here, if I go in 1 hour increments, whoops, you can actually use the Big Dipper as a clock. You could say, okay, well, let's say that the Big Dipper were here at 9 p.m. And then you get knocked over the head, and then you wake up and you don't know what happened. Maybe you fell off a waterfall or something. And when you get back, when you wake up, you see the Big Dipper is pointing like this, but it was over here before. So the Big Dipper went through a 90-degree angle, but 90 degrees is 1/4 of a circle. And so this thing is going to go all the way around each day because of the Earth's rotation. So it's the Earth's rotation that's making this apparent motion of the stars around Polaris. If you turned off the Earth's rotation, then the stars would cease to move. And so by looking from here to there, if we see that the Big Dipper has gone from here to there, and that's 90 degrees, then we can conclude that's 1/4 of a day, or that 6 hours had gone by. And so by calibrating the Big Dipper at a certain time, you can actually use it as a clock to determine what time it is at some later time. And so this is the basic motion then of stars um, um, nearby to the North Star. So we'll keep going here. And we'll notice this line too. Now this line is called the ecliptic plane. And so the ecliptic plane is the plane that contains all of the planets and the zodiac constellations, but it's also the path that the sun seems to take during the daytime. And so you can follow the path of the sun during the daytime, and then when it gets to be night, well, notice here, there are some planets, but we can't see them during the daytime, but they're actually out. Jupiter and Saturn are out during the daytime. We just can't see them because the sun's putting out too much light. But now the sun is about to set. Okay, now it's nighttime, but still, do you see there's Jupiter and Saturn? So it's kind of almost raining right now, but you could go out as soon as the sun sets, which isn't too far away from now. And if it were clear, you'd probably see Saturn pretty close to the horizon and Jupiter fairly high up in the sky. And so the basic motion then along the ecliptic plane is the same for the planets at nighttime as it is for the sun during the daytime. And so if you can follow that path that the sun takes during the daytime, that's also the path that the planets take at night. And so then you can see Jupiter. And so that Jupiter ends up setting somewhere around 12:30 midnight. Uh, Now, you can look here by moving this window around. This is something you can do because you have this interactive program just to kind of get used to how you view things. This is what you would see from the surface of the Earth as you look in these different directions. So you're looking in a somewhat northerly direction here, you'd be facing north. And then if you want to look higher in the sky, you can go up like this until you get to Polaris or the Big Dipper, or there's Polaris there. Polaris is the tail star of the Little Dipper. And then you can look from different directions. Now you'd be facing northeast. This is what you'd see in the sky. This is what you'd see if you go up higher. And so the basic motions here, these are things that you can play with just to get used to this. But the basic motions then are that the stars tend to move in counterclockwise circles around Polaris each day. And the zodiac constellations, which contain the sun, the ecliptic plane is the path the sun takes during the day, but the zodiac constellations at nighttime are going to be markers for the locations of planets. And so the planets will be in front of, say, Aries or Taurus or Gemini. Right now, Jupiter is right in front of the constellation of Aries. And so you can get an idea then of planet positions just by following motions along the ecliptic plane. Okay, so these general motions then, if I can go here, the general motions in the sky, stars describe counterclockwise circles around the North Star each day. And here's a time-lapse photo of uh, this is up in northern Alaska in the deepest part of winter, so that the sun never rises, so that you can get a full 24-hour view of the stars. This is an overexposure of the stars that are going around the North Star. And so this helps to illustrate what we were saying about the general motions of the stars in the sky. These are the way the stars appear if you're up in the Arctic. Near the horizon, they tend to move horizontally. Near the equator, they tend to move vertically because the sun, the North Star is right on the horizon, and the stars tend to move in counterclockwise circles. And so when you get to the horizon, they're moving up and down. And they tend to move. So when stars set or rise, they tend to move along diagonal paths, which is a combination of the horizontal motion that you would see up near the poles and the vertical motion, which is what you see down near the equator. Now, you don't need to be experts in all of this to gather the data that we're talking about, but this is just some background information. This is something you can go back over if you're interested in it. And I've given you way more information than you really need to gather the data and to do your research. But in the limited amount of time that we have, I just want you to have a little better rounded feeling for the basic principles of astronomy and how the sky works. Okay, and then the zodiac constellations are basically markers along the ecliptic plane. And so uh, and normally you hear about zodiac constellations from, say, astrology, somebody's sign. What does that mean? Well, 2,000 years ago, uh, the sun was directly in front of the zodiac constellation Pisces. And so my birthday happens to be on March 11th. And so I was a Pisces 2,000 years ago. But in 2,000 years, the Earth's rotational axis has shifted the whole situation by one zodiac constellation. And so this is what you are today. This is at the moment of your birth. This is where the sun was located with respect to the background constellations. And so although astrology gave the impetus, as we learned last time, for the data that was gathered. There were so many kings that wanted important information about when a planet was going to be in retrograde motion, like Mars, that created the impetus to get information about the sky. But the science of astrology has a few holes in it because the astrologers haven't bothered to update their charts in 2,000 years. Okay, so here's a summary of the daily motions then. Each day, the stars near the North Star make complete counterclockwise rotation. At night, along the ecliptic plane, zodiac constellations and planets seem to rise in the east and set in the west, and the sun follows the same east to west pattern along the ecliptic plane each day. And so let me finish up then by just looking at, let's see here if I can find a simulation. There we go. So this is from Unit 1. And so let's just go back to, where would that be? It's angular measurements. And so these are things I'm going to be talking about next week in terms of the celestial sphere, right ascension, declination. We'll also talk a little bit about telescopes next week. Here's the motions in the sky. So those are all those PowerPoint videos that I was showing you. And oh, here we go. Okay, so here is a time-lapsed view of planets rising and setting. So this would be setting, following the path of the along basically along a diagonal path. Remember, we said that near the horizon, stars tend to move along diagonal paths. So this would be in the direction toward the west. Now this is looking toward the east. Now we're looking along the ecliptic plane. There's Jupiter rising. Jupiter, this time of the year, actually rises around noon. So during the main part of the day, we wouldn't be able to see this. But when this video is taken, all of the planets were rising before sunrise. So here's Mars. Notice that they're all following that same basic path. That's the same path that the sun will take during the daytime, the ecliptic path. Saturn, Moon, Venus. Okay, now this is accurate. For this time of the year, if you're interested, you'll see Venus rising just before sunrise in the east. So you'll see that. And also Mars should be visible just before the sun comes out. So you should be able to see Venus maybe a little bit higher than this in the sky just before sunrise. And then Mars will just possibly be visible in the morning sky. In the evening sky, expect to see Jupiter pretty high in the sky when the sun sets, but then it will be setting in the west along that same path that the sun takes around 1 a.m. And of course, as the sun rises, the uh, it's impossible to see any of those other objects unless the sun's light is blocked during a total eclipse, which isn't very common. Okay, so we've covered a fair amount today. We've looked at the physics of what happens when stars go into elliptical orbits, how that relates to the basic laws of planetary motion. We looked at the main driving force of gravity, which is an inverse square law, and how that relates to orbital motion. We looked at how the sky works in terms of just basic things that happen. Because of the rotation of the Earth, the sky tends to move in counterclockwise circles about the North Star if you're nearby to the North Star, but farther away. If you're near the ecliptic plane, the stars tend to rise in the east and set in the west along the ecliptic plane in just the same manner as as the sun does during the daytime. And so go ahead, if you want to look ahead a little bit, we'll be doing telescopes next week. We'll also look at celestial coordinates, which is really important because when you pick out your binary star system, it will be in terms of those celestial coordinates. And we'll also have an opportunity to take a look at the specifics of binary stars and um, maybe get a little bit into the actual process by which we will be selecting our star in each of our research groups. Are there any questions?
Did we already pick out our research groups?
I'm sorry?
Did we already pick out our research groups?
No, the research groups, I'm going to give you a questionnaire next week, and then I'll try to match you up in research groups. And if you have any preferences in that questionnaire, you can let me know what they are, and I'll try to match you up based on your preferences and who seems like they would be the best fit with other people if you don't have preferences. Are there any other questions?
I think there's a question in the chat that just popped up.
Okay, it's hard for me to keep track of these things and look at chat at the same time.
It says
Can
how
you
big are
ask the
the
question?
groups?
I'm
It says
sorry.
the question it says is how big are the groups going to be? Like 3 people?
I think that we could make it 4. I think 4, or it depends. You could have 5 people in a group, but if your preference is to have a smaller number in a group, that would be okay too. It depends a lot on how much energy you want to put in, how high up um, on the list of writers, authors of the paper you want to be. There are uh, functions that each person can have, and I think that they'll naturally tend to align themselves with the things that you feel the most comfortable with and that you like to do the most. And so there should be a good writer on each group because getting the thing published is super important, and being able to take information and write it down in a coherent way is really important. Then there are going to be people that are going to be better with computers that uh, you might need if you run into a snag somewhere when you're trying to download something or upload something or make something work or get something plotted. So somebody that can do computers that would be a very important function within a group. You would also want people that would go in and search through the various parameters that we have. With there's certain range of magnitude that you would want. There is a certain separation distance between the stars that you would want, so that you can see the two stars, you can measure their distances apart, and you can see both of them in a picture that would be taken by the automated telescope. And uh, there would be a little bit of searching that would take place. And so somebody that would want to do that kind of research would be very valuable in a team. Somebody might want to do the data analysis, in which you take the data, say from 10 pictures, and uh, you find the standard deviation and the standard error on them. And so some people would be uh, able to handle more than one of these jobs, but it would depend on how much time you have available to put into it, and how and your contribution would be proportional to how high up in the author list in the publication that your name would appear. So there's some flexibility with that. So some people might want to do most of it themselves and be in a group of two, and so that's something that we can explore when I pass out the questionnaire.
Yes, thank you.
Okay, sure. Are there any other questions? Okay, well, then I'll see you next week or sooner if you want to stick around after after everybody else signs off, or if you want to come by during my Zoom office hour next Monday. Otherwise, we have a few quizzes that are scheduled for this week. You can find them by going uh, by either just clicking on it, and it'll show you when it's due, or by going to syllabus and then just scrolling down, and it'll show you which ones are due at which time. So if it turns out that you have some kind of a time commitment and need to have something postponed, I'm somewhat flexible with that, and so you can just shoot me an email and let me know if you have any problems completing the quiz by a certain date. But basic idea is to just go through, what I discussed, look at the videos and any reading that was recommended for that particular quiz, and then just take the quiz.
I have a question about the quiz. I think last week when we met, you said you were gonna make the quizzes be on on multiple attempts, and I only had 2 attempts.
Okay. How many attempts do you think I should I can't there's some people had already taken those first quizzes, and so I couldn't
Yeah.
switch. I couldn't
Yeah, I
switch
take it.
those once somebody started to take them. But in terms of
Oh,
the future ones, what's your feeling about that? Would you like what, 2 attempts, 3 attempts?
yeah, no, that sounds good. I just was curious because of the first ones I went back and I wasn't,
Right.
yeah.
Yeah. With the first ones, once somebody has taken it, I can't switch it. And so we'd already been at a point where people had taken those first two. But I can go back in and adjust the number of attempts for future ones.
Okay.
You're gonna do 3?
Does that sound good to you?
Yes, yes, it does.
Okay. That's what I'll do.
So you're gonna start doing 3 attempts instead of 2 for future ones?
Yeah. Yeah. I'll go through, and as long as nobody's taken those quizzes, I'll switch it from 2 to 3.
I've taken them and did what you asked to do. And I know that last time you had, sketches that you wrote on the lecture. Did we not have that with this one?
I'm sorry?
You didn't have, last time I took screenshots of the lectures that you wrote, and you didn't have any of that in this lecture?
Well,
Notes?
I did more visual stuff this time.
Okay,
If you, in terms of taking notes, you could take notes from the visuals. It's hard for me to switch back and forth and be constantly writing and then trying to have a smooth
you
presentation.
don't,
We had
you
a lot,
don't have any, you don't
we had a lot
record
more
any of the
animations and
lectures?
things I'm sorry, we had a lot more animations and things this time,
I'm
and
sorry, do you record any of the lectures?
they're all recorded and they're all on there, right on the front homepage. So you can
Okay,
go back over those anytime you want.
okay,
Yeah, yeah. So I record all of them. Yeah, yeah. And
okay.
so you can go back through, you can pause it, you can write things down. And so if you didn't feel like you took good enough notes, you can go back and check it out and follow through with it as many times as you want.
I read in your notes that we possibly would be doing some viewing out tonight. Did that happen or no?
Viewing
Night viewing? Not yet?
with the simulation, the star chart that I showed you. That,
Okay,
It's raining right now, and it would be hard for us to go outside and to
oh,
do a Zoom lecture. So I don't know how that would work. I don't
okay.
think
Yeah, I'm in a different area and it's not, so, but I know we had that weather forecast, so I just was
Well, it would
following
still
up.
be hard to go outside if we're in a Zoom lecture.
Right,
Yeah, so I don't think that's an option for us here.
okay.
Any other questions?
I have a question.
Yeah.
I sent you an email because I took the quiz late, so I was wondering if I could get full credit.
You took it late?
Yeah, like I sent you an email, like I said I was sick. Well, it's in the email, but I literally took it like 20 minutes after like the due date.
Okay, I extended the due date.
Oh, okay. Let me check my grade.
Yeah. I extended the due dates because of the students that weren't able to add yet. And so I pushed them off a little bit. But for the people that are still wanting to officially add, I can individually give you a couple more days once you're officially enrolled, because you won't be able to take the quizzes, but you can view, what all of the resources until
Uh,
that.
I just checked my grades and it says quiz 1 and 2 was due January 31st. But can I get like full credit because I took them late.
Were you penalized?
Yes, I was.
Okay, can you figure out how much you were penalized, and I'll just manually change your grade.
Yeah, one of them is penalized by like 3 points, and the other one is just 1 point.
Okay, would you just shoot me an email with that information, and then I'll take care of that for you?
Yeah, I sent you an email like last night.
But
just so you
specifically,
can-
if you could send one with the number of points.
Yes.
Okay, good.
What happened with that? She got penalized for what?
It was late. You can
Oh,
still
okay.
open up the quiz, but you're penalized if it's late.
Oh, okay.
I think you can still access the quizzes, but I can fix that in the future so that that you don't get penalized. It just does it automatically.
How many can we take? Just two each? And then they give you the medium of that?
I don't understand
You
your question.
You can take two attempts and then you get the average of both? You get the average of both because you only get two attempts, correct?
I don't think so. I think you just if you get it right, then it's right.
I think it keeps your highest score
Yeah, keeps
all
your
the times.
yeah, it doesn't average them.
Okay.
Well, thank you.
Okay, sure.
I'm gonna go.
See you
Have a good
next
night.
week.
Okay, thank
Bye.
you. Bye.
Take care.